All right, hopefully third time's the charm. You don't know this, but I've tried to make this video several times and I keep failing because I keep coming up with functions where things don't work out quite how I want them to work out. Hopefully this time I'll be able to illustrate the point that I'm trying to get across in this video, which is sometimes it's hard to figure out what your variable of integration should be in these 6.1 problems where you're trying to figure out the area bounded by two different curves. We kind of got a glimpse into that in the last video when I chose two curves and I showed how to integrate this with respect to y and also with respect to x. And we did it both ways. It got the same answer both times. And at the end, I left you with this statement that was like, yeah, this time it worked both ways, but you really do need to know how to do it both ways because it's entirely possible that I give you an example that only works one way or the other. Well, here's that example. Suppose you want to find the area bounded by these two different curves. It turns out this can be done completely algebraically. You could do this without the graph of the two different curves, but it's a lot harder that way. I think the part that really becomes harder if you try to do this purely algebraically is determining your variable of integration. There's a way to do it without the graphs, but for the purposes of our class, let's just suppose you'll always have the graphs handy. And you're like, but what if I don't have a graphing calculator? If this is ever a test, I'll provide you with the graphs. I'll go into Desmos and I'll graph the two functions just like I did here, and I will show you exactly this. So what you want to be able to do is analyze this picture and tell from this picture what your variable of integration needs to be. So in blue, I have the curve y equals the cubed root of x, and in red, I got 2y squared minus 4y plus x minus 8 equals 0. So determining your variable of integration, I think the easiest way to do it is if your variable of integration is x, then you're thinking vertical rectangles, right? That's everything we've done so far in this class. Our variable of integration has always been x, and we've always thought about calculating these areas by using infinitely many vertical rectangles to fill up the region. And what we just learned new in this chapter is that, well, if it's the area bounded by two different curves, we can just subtract the two definite integrals. But you have to be really careful. That only works if each of your vertical rectangles goes from one curve to the other. So what I'm saying is if you pictured a vertical rectangle right here in this bounded region, the bounded region is kind of this area here, that rectangle would go from blue to red, right? The blue one is up on top, the red one is down on the bottom. You can picture that rectangle. It works fine over here or over here or over here. But if you get way out to the right here, things break down. If you try to picture a vertical rectangle that would fill up this bounded region, if we're way over here to the right, that rectangle would span from red to red, which is problematic. That goes against the formulas we derived in the previous video. Because we cannot fill up the bounded region with vertical rectangles that span from one curve to the other, that means x cannot be our variable of integration. For y to be your variable of integration, you got to think about horizontal rectangles. But then you ask yourself basically the same question. Can I fill up this bounded region with horizontal rectangles where every single horizontal rectangle would span from the blue curve to the red curve? And I think the answer to that question is yes, right? You could picture a bunch of rectangles down here and they keep going and each one appears to go from blue to red. All the way up here, we could fill up the whole region with rectangles that span from blue to red if those rectangles are horizontal. And for horizontal rectangles, you're thinking y is your variable of integration. So the big takeaway is that we have to integrate with respect to y. Here's my best attempt at copying the graphs that we saw in Desmos. It's not nearly as pretty, but hopefully it's good enough for us to reference to kind of look at what the pictures are. In red, we have this curve. In blue, we have this curve, and that gives us this green bounded region. So since we're going to integrate with respect to y, when we set things up, we're going to want our variable of integration to be a y. That's kind of the good first step. And once we figure out that our variable of integration is y, we know that our bounds got to be y values and that we only use the variable y when we express our functions here when we subtract the two of them later on. So first things first, let's figure out our bounds of integration. If we want to figure out our bounds of integration, we want to solve for y equals some number. And to solve for y equals some number, we have to get rid of all the x's. So sort of the trick is, kind of counterintuitively, if you want to solve for your bounds in terms of y, you first solve the two equations for x. So I solve this equation for x. That's easy enough. I could add the 8, add the 4y, and subtract the 2y squared from both sides of the equation. And that would give me x equals negative 2y squared plus 4y plus 8. And then to solve this equation for x, I'd have to cube both sides of the equation. And I would get that x is equal to y cubed. And now the idea here is, since both these equations are solved for x, I can set the two x's equal to each other, and that will make a new equation which will only have the letter y. And that's the good thing. We only wanted the letter y because we want to solve this for y, so we kind of get rid of the x's. So if this is equal to x and this is equal to x, then this equals this, and I get that y cubed is equal to negative 2y squared plus 4y plus 8. which is a third degree polynomial, which generally I won't ask you to solve, but I picked the numbers really carefully here to make sure that things could work out. What we want to do is first set it equal to 0 and then factor. So let's add 2y squared to both sides of the equation, and then subtract 4y from both sides of the equation, and subtract 8 from both sides of the equation. That gives us this third degree polynomial, but I think this one will work that we can factor it by grouping. And again, I'm not going to ask you to solve third degree polynomials on any tests or anything, but maybe you can just stick with me for this example. So we look at our first two terms here, we notice they have a y squared in common. And if I pull the y squared out from these first two terms, I'm left with y plus 2. And that becomes what I refer to as a target. I want to pull something out of my next two terms, so I'll be left with a y plus 2. Well, if I pulled out a negative 4 from these next two terms, I'd be left with a y plus 2, because negative 4 times y plus 2 gives me negative 4y minus 8. And what I now have are two terms, and each of those terms have a y plus 2 in them. So I can pull out that y plus 2, and all that's left behind is this y squared and this negative 4. And the nice thing about y squared minus 4 is it's a difference of squares, so it factors as y plus 2 times y minus 2. And now what I can say is, well, this whole thing will equal 0 if this equals 0, or this equals 0, or this equals 0. Well, these are the same. Y plus 2 equals 0 when y equals negative 2, and y minus 2 is equal to 0 when y is equal to positive 2. What I'm saying is negative 2 and positive 2 are the two y values at which these two curves intersect. This is negative 2, and this right here is positive 2. And you might have been able to get that off the graph on Desmos, but I can always turn off the axes in the grids, and then you wouldn't be able to tell what these values were, and you'd have to solve for them algebraically. So it's a good idea to be able to solve for them algebraically. Just know that I won't ask you to solve third degree polynomials like I did here. At any rate, what we just figured out are that our bounds of integration are going to be from y equals negative 2 to y equals positive 2. So I'll write negative 2 and positive 2 here, but you're thinking y values because we wrote this dy here. And now what I want to do is look at my two curves and ask myself the question, which of the two curves is further right? It's not which one is on top and which one is on the bottom. It's which one is further right and which one is further left. You can think about it as which curve has the larger x values in the region we're interested in, and which one has the smaller x values in the region we're interested in. In this region that we're interested in, the red curve has the largest x values. The red curve is the one further to the right. So we want to do the red curve minus the blue curve. And when I write the red curve minus the blue curve here, I better be really careful, and I make sure that I express both the red and the blue curves with only the variable y, because my variable of integration is y. So I don't want to write some expression like this that has both y's and x's in it. What I instead want to write is this, which represents the x value of this function just in terms of the y value. So I got negative 2y squared plus 4y plus 8 representing the red function, and from that I want to subtract the blue function, which is represented by y cubed, and that leaves me with an integral to evaluate, and if I could evaluate this integral, I'd be done with this problem. The good news about evaluating this integral is it's just a polynomial, so all we're doing is using the power rule here. First, I want to take y squared and make it y cubed, but then I got to remember I have to multiply by a third in order to make the coefficients match. I'm going to change this y into y squared, but then I have to multiply by 1/2 to make all the coefficients work. I'll tack on a y here, and then finally the antiderivative of y cubed is the 1/4 y to the 4th power. And this is what I need to evaluate from negative 2 up to positive 2. It's a little bit tedious to plug in the numbers, but I think we can do it. 2 cubed is 8. 8 times negative 2/3 is negative 16/3. 2 squared is 4, and 4 times 2 gives me 8. 2 times 8 gives me 16, and then 2 to the 4th power is 16, and 16 times negative 1/4 is negative 4. And then if I plug in negative 2, some of those values will repeat, which will be kind of nice. Negative 2 cubed is negative 8. Negative 8 times negative 2/3 is positive 16/3. Negative 2 squared is positive 4, and 4 times 2 is 8, just like it was earlier over here. Negative 2 times positive 8 gives me negative 16. And finally, negative 2 to the 4th power is positive 16, which times negative 1/4 gives me negative 4, the same thing that I have over here. This negative 16/3 minus this positive 16/3 gives me negative 32/3. This 8 minus this 8 cancels out. This 16 minus this negative 16 gives me positive 32. and this -4 minus this -4 cancel out, what I get left with is just -32 plus 32. And I think if you get a common denominator, you'll have 96 thirds here, and 96 minus 32 is 64 thirds, which will be the area of this bounded region. All right, one last thing I want to show you. I think I can just reuse this example to kind of add on one more concept without actually doing a whole nother example. Instead of being asked to just find the area bounded by these two curves, maybe you'll run into cases where you're asked to find the area bounded by four curves, right? We have this same curve, 2y squared minus 4y plus x minus 8 equals 0, and y equals the cubed root of x. Those were the two we saw above. But then we also got y equals -1 and y equals +1. And it appears that this would make the problem more challenging, but it turns out it doesn't. And you can see that if you just graph it in Desmos. So we still have the blue curve and the red curve, but if I add y equals 1 and y equals -1, you see that those are just horizontal lines. And so if I think about the region bounded by all four of these guys, is kind of the region in here now, right? It's almost the same region I figured out before, except I don't want this part anymore, and I don't want this part down here anymore. I just want this area in between. And so what we'll do here is we're still going to use horizontal rectangles. It's just now we don't have to worry about our bounds of integration. We don't have to think about our bounds of integration starting at a y value of -2 and ending at a y value of +2, because by supplying these two lines, y equals -1 and y equals +1, really what the problem is telling us is our bounds of integration. Right? We can see that our horizontal rectangles will start at a height of -1, and they'll keep going until we get up to a height of +1. So sometimes you'll see problems that add on things like y equals -1 and y equals +1. And that really tells you two pieces of information. It tells you that your variable of integration is going to be a y. And then it also tells you that the bounds on that variable of integration will be -1 and +1. So you won't have to go through this step where we solved for the bounds of integration. We'll set up our integral almost identical to this, except there'll be a -1 here and a +1 here. Our antiderivative will be the same, and we'll get slightly different values when we plug in 1s and -1s as opposed to 2s and -2s. I'm kind of burnt out on this section, so I think I'm going to not even calculate those answers and just leave the rest as like an exercise for you to complete if you feel like it, and maybe we'll just call this good.